Good morning, students. In the last class, we have seen the electric field at a point due to dipole on an axial line and the electric field at a point due to dipole on an equatorial line. Now, we will see the relation between these two, that is axial line and equatorial line. Now, we will see the relation between the electric field at a point due to dipole on an axial line and the electric field at a point due to dipole on an equatorial line. We already know the equation. The electric field at a point due to dipole on an axial line is given by 1 by 4 pi epsilon naught 2p divided by r cube, right? And also we know that the electric field at a point due to dipole on an equatorial line is given by E is equal to 1 by 4 pi epsilon naught p by r cube. So using these two relations, so I am going to derive a relation between the electric field at a point due to dipole on the axial line and an equatorial line. Now what I am going to do is I am going to rewrite this equation 1. So it becomes EA is equal to 2 into 1 by 4 pi epsilon naught p by r cube. So what I have done here, I have just rewritten this equation 1. Now this 1 by 4 pi epsilon naught p by r cube is nothing but it is an expression for the electric field at a point due to dipole on an equatorial line. So I will replace this here, I will replace this by EE. So I have kept 2 as it is. So this equation, so I am going to replace it by electric field at a point due to dipole on an equatorial line. So this equation reduces to EA is equal to 2 times EE, that is the electric field at a point due to dipole on an axial line is equal to 2 times the electric field at a point due to dipole on an equatorial line. Now after seeing this, now we move on to the electric field at a point due to dipole at any point. So if I want to find out the electric field at a point on a dipole, so we can use a general case and we can find out at any point. So what is that equation is given by? The equation is given by E is equal to 1 by 4 pi epsilon naught p square root of 1 plus 3 cos square theta divided by r cube. So this is the general equation. What is the equation? E is equal to 1 by 4 pi epsilon naught p square root of 1 plus 3 cos square theta divided by r cube. So using this general case, I will derive an expression for the electric field at a point due to a dipole on an axial line and an equatorial line. Why? Because we know that on an axial line the angle will be theta will be equal to 0, right? So I am going to substitute theta is equal to 0 in this expression here in the place of theta. So what happens to the equation? E is equal to 1 by 4 pi epsilon naught p square root of 1 plus 3 cos square 0 divided by r cube. We know that cos 0 is equal to 1. What is cos square 0? Again it is 1. So this equation reduces to 1 by 4 pi epsilon naught p square root of 4 divided by r cube. What is square root of 4? Square root of 4 is 2. So E is equal to what we get? 1 by 4 pi epsilon naught 2p divided by r cube. So this equation we already know. This is an equation for the electric field at a point due to dipole on an axial line. So we have derived this using this general case, right? So now I will put theta is equal to 90 degree. So that means if theta is 90 means it is the point will be at an equatorial line. If the point lies on an equatorial line, we can write theta is equal to 90 degree. So same thing, I am going to substitute theta is equal to 90 degree here in the place of theta. So the equation reduces to E is equal to 1 by 4 pi epsilon naught P square root of 1 plus 3 cos square 90 divided by r cube. What is cos 90? Cos 90 is nothing but it is 0. And what is cos square 90? Again it is 0. 0 into 3, it is 0. So only thing that remains is square root of 1. So the equation reduces to E is equal to 1 divided by 4 pi epsilon naught P divided by r cube. Again we know this equation. What is this? This is an equation for the electric field at a point due to dipole on an equatorial line. Next we will see the torque experienced by the dipole kept in an uniform electric field. So before that we will understand what is torque is. For example, if I have a body, so if I apply a force, if this body experiences a net force, this will undergo a linear motion. For example, if I apply a force here, so what happens to this? It will move. But if the same body, if it experiences a equal and opposite forces, then the net force will be equal to 0. But it will not undergo a linear motion, but instead this body will rotate. For example, if I apply one force along this side and another force along this side, both are equal in magnitude. If I apply two equal and opposite forces which are equal in magnitude, but it will be acting on the opposite directions. So what happens like this? One force is acting like this, and the same magnitude of force another is acting along this direction. So what happens to this? This body will rotate, but the net force will be equal to 0, but this body will undergo a rotatory motion, right? So it experiences a moment of couple called as torque, so which you can see in a rotating fan or a pottery wheel, etc. Now we will see the torque experienced by the dipole, so kept in an electric field, and we derive an expression for torque. Now see here, I have kept a dipole, right? I have kept a dipole in an uniform electric field. Now this dipole, if it is kept in an electric field, I told you it will experiences what? A equal and opposite forces. We know that F is equal to EQ, and we know that E is equal to F by Q, and what is F? F is nothing but E into Q. Now this dipole has two charges, equal and opposite charges. It is, one is plus Q and another is minus Q. This plus Q will experiences a force, that is F is equal to EQ along the direction of electric field. This is the direction of electric field. So this charge will experiences a force along the direction of electric field, because the electric field is made up of two charges. For example, this will be plus Q here and this will be minus Q. So this charge will be attracted towards this minus Q, and this plus Q will repel this plus Q. So therefore what happens? This charge plus Q will experiences a force along the direction of electric field. Now coming to this charge minus Q, so this minus Q will experiences a force, that is F is equal to EQ, so it will be opposite to the direction of electric field, because again, so this electric field line is made up of plus Q this side and minus Q on the other side. So this is minus Q, it will be attracted towards this plus Q, and this minus Q, which will be here, it will repel this. So therefore the force experienced by this minus Q will be opposite to the direction of electric field. So due to this, the equal and opposite charges this dipole will experience a moment of couple called as torque. That means this dipole will rotate. Now, what is this torque? This torque is nothing but, it is the magnitude of either force into the perpendicular distance between the two parallel forces. So what is torque? So torque is nothing but the magnitude of either force into the perpendicular distance between the two parallel forces. Now, the magnitude of either of force, this charge is experiencing a force of F is equal to EQ, and this is experiencing a force F is equal to EQ, but it will be in the opposite direction. So we have to take only the magnitude. So what is the magnitude of that? So it is nothing but E into Q. You can take the magnitude of this force or this force. It is one and the same. So, and what is the perpendicular distance between two parallel forces? See, this is a force experienced by the charge. What is the perpendicular distance to this force? This is the perpendicular distance, right? And this is a force here. If I take the magnitude of this force, what will be the perpendicular distance for this? Again, this is a force and this will be the perpendicular distance. So, I will write here, torque is equal to the magnitude of either of a force, I write it as F, into what is the perpendicular distance? Perpendicular distance, if I take this force, the perpendicular distance will be BC. Or if I take this force magnitude, the perpendicular distance will be, again it is BC. So I will write F into BC. Now, I know this, F is nothing but E into Q. Take the magnitude of this. So this is nothing but F is equal to E into Q. Into, I should now calculate this perpendicular distance. To calculate this perpendicular distance, I know the angle made by the dipole with the electric field is nothing but theta here. What is theta there? Theta is the angle made by the dipole with the electric field. Now, using this triangle, I have a triangle here, that is A, B and C. Using this triangle, I will see what is sin theta is. What is sin theta from this diagram? So sin theta is nothing but, it is opposite side by hypotenuse. So this is theta. So opposite to this is opposite side. And this is 90 degree. Opposite to this is hypotenuse. So what is sin theta from this? Sin theta is nothing but, it is BC, opposite side, and divided by BA or AB. So here, from the triangle ABC, I have taken sin theta is nothing but BC divided by AB. BC is opposite side and AB is the hypotenuse. Now, I know what is this AB is. AB is nothing but 2A. That is the distance between the two charges. So, this AB can be replaced by 2A here. So, I am going to replace AB by 2A. And now, I will cross multiply this 2A here. So, what happens to this? BC is equal to 2A sin theta. If 2A sin theta, if I send here, so I will get BC is equal to 2A sin theta. Now, I am going to substitute this here in the place of BC. So now what the equation reduces to, tau is equal to, that is torque, is equal to, F is nothing but E into Q, we know this, and what is BC? It is 2A sin theta, correct, right? Now, we know the expression for dipole moment. What is the expression for dipole moment? P is equal to Q into 2A. So now, I can replace, no, see here, I have 2A here, and I have Q here. So this can be replaced by P. So we know this, the dipole moment, expression for dipole moment is nothing but P is equal to Q into 2A. So in this equation, I am removing Q into 2A and I am replacing it by P, dipole moment. So what the torque will become? Tau is equal to, it is EP sin theta or PE sin theta. So this is the expression for torque experienced by the dipole kept in an uniform electric field. Now, How to write this in vector form? See here, we know this A cross B is nothing but AB sin theta. This is vector product. So A cross B can be written as AB sin theta. Now look at this equation here. We have tau is equal to PE sin theta. So now in vector form, I can write this as, we have this tau is equal to, it is PE sin theta. This can be written as tau is equal to, it is P cross E. Right. So what I have done, I have used the equation tau is equal to PE sin theta, and I am going to write this in vector form. We know that A cross B is nothing but AB sin theta. So I am comparing with that. So tau is equal to PE sin theta. So this PE sin theta, it is similar to this, correct? So if AB sin theta can be written as what? A cross B. Therefore PE sin theta can be written as, it is P cross E. Now we will see the cases, special cases, if a torque experienced by the dipole kept in an uniform electric field. So for example, if you have theta is equal to 0, what is the meaning of that? If theta is equal to 0 means the dipole is along the direction of electric field. What is theta is 0 means? The theta 0 means the dipole is along the direction of electric field. We know this, tau is equal to PE sin theta. Tau is equal to what? PE sin theta. So what is the angle between these two now? Theta is 0. Substitute 0 here. So this becomes tau is equal to PE sin 0. What is sin 0? Sin 0 is 0. Therefore the tau is equal to 0. So I repeat. Now I am placing a dipole along the direction of electric field. If I place like that, so what is the angle between these two? The angle between these two is 0. So substitute in the expression of torque experienced by the dipole. So torque is equal to PE sin theta. We know this. Now what is theta now? 0. Substitute here in the place of theta. This becomes tau is equal to PE sin 0. Sin 0 is what? 0. So 0 into anything is again 0. The torque experienced by the dipole, if it is placed along the direction of electric field, so it is 0. It will not experience any torque. Now let's move on to the second case. What I am going to do is, I am going to rotate this dipole by an angle of 90 degree like this. So that means the dipole now I have rotated by 90 degree, right? So now I can say the dipole is actually perpendicular to the direction of electric field. That means theta will be equal to how much? 90 degree. Now what I have done, I have rotated the dipole, right, by how much? By 90 degree like this. Then I can say now the dipole is normal or perpendicular to the direction of electric field. Then what is the angle between the dipole and electric field now? 90 degree. So I will substitute this 90 degree in this expression, in the expression of torque. Tau is equal to PE sin theta. Substitute 90 here. Now what happens to this? What is sin 90? Sin 90 is 1. So 1 into PE. So what I get? Tau is equal to P into E. Now that means if the dipole is perpendicular to the direction of electric field or normal to the direction of electric field, it is experiencing a torque. What is the torque experienced by that? That is tau is equal to PE. That means it experiences a maximum torque when tau is equal to, that is tau is equal to PE when the dipole is perpendicular to the direction of electric field, and it experiences a minimum torque when the dipole is along the direction of electric field. right? Now, so what I do now is, in the next case, I am going to rotate this dipole by 180 degree. That means, see here, now the dipole actually it was like this and I have rotated by 180 degree. Now, what is this? Now the dipole actually it is opposite to the direction of electric field. The dipole is how it is placed? It is placed opposite to the direction of electric field. That means theta is 180 degree. So again we know the expression for torque, that is tau is equal to PE sin theta. So now I am going to replace theta by 180 degree. What is sin 180? Again it is 0. So 0 into anything is 0, tau is equal to 0. That means the dipole will not experience any torque when it is placed opposite to the direction of electric field. Next, in the next step, in the next case what I am going to do is, I am going to rotate this dipole by 270 degree. Actually dipole was like this and I am going to rotate it by 270 degree. So I have rotated like this, 270 degree. So the angle between the dipole and the electric field is now how much? 270 degree. So I will substitute this 270 degree in the place of theta here. So now what is the expression of torque? Tau is equal to PE sin 270. What is sin 270? It is minus 1. So it becomes tau is equal to minus P into E. So I repeat, now what I am going to do now, so I have rotated this dipole by an angle, dipole actually it was like this and I have rotated it by 270 degree. If theta is 270 degree, that expression for torque will be, so that is tau is equal to PE sin 270. So sin 270 is nothing but minus 1. So the expression becomes tau is equal to minus P. Now in two cases it is experiencing a torque. Which are the two cases? One is when the dipole is normal or perpendicular to the direction of electric field, that is when theta is equal to 90 degree, and if the theta is equal to 270 degree. When the theta was 90 degree, it experienced a force, tau is equal to P into E. When theta is equal to 270, it is experiencing a torque, that is tau is equal to minus P into E. Now both these cases, that is case 2 and case 4, they are not in equilibrium because it is experiencing a torque. When theta is 90, it is experiencing a torque of tau is equal to P into E, and when it is 270 degree, it is experiencing a torque of tau is equal to minus P into E. These two cases, now they are not in equilibrium. But when theta is equal to 0 and theta is equal to 180, the torque experience is experienced by the dipole is 0. You can see here. When the dipole is along the direction of electric field and when the dipole is opposite to the direction of electric field, dipole is like this and electric field is like this. In both the cases, the torque experienced by the dipole is 0. Now I can say in these two cases, that is case 1 and case 3, where the torque experienced by the dipole is 0, so therefore I can say these two are in equilibrium. Which are in equilibrium? That is when the dipole is along the direction of electric field and when the dipole is opposite to the direction of the electric field. So I can say that in these two cases, the torque experienced by the dipole is 0, therefore they are in equilibrium. But there is a small difference between these two. Of course, this is in equilibrium, and in this case also the torque experienced by the dipole, so it is again is in equilibrium. But there is a small difference between this, that is case 1 and case 3. What is that difference? Now, for example, this is a dipole which is placed along the direction of electric field. So actually it is like this. So for example, I have a dipole like this So the direction of electric field is along the direction of a dipole. Now I disturb this. If I disturb this, so what happens? It comes back to the same position, right? So what I am doing, I am disturbing the dipole. So if I disturb the dipole, so what happens? If it comes back to the same position, right, by itself, then I can say the dipole is in stable equilibrium. For example, now the dipole is like this, right? So I will rotate like this. So this is one force will be acting like this, another force will be acting like this. So what happens? If the force is removed, then what happens? It comes back to the same position as it was. So in this case, if theta is equal to 0, this I can say this is in stable equilibrium. Right? This once it was asked in an exam. And going back to this here, if theta is 180, that is if the dipole is opposite to the direction of electric field, then also the torque experienced by the dipole is 0. This is also in equilibrium. So now we should know actually whether this is in stable equilibrium or unstable equilibrium. We know what is stable equilibrium. If the position of the dipole is disturbed, what happens? Again it comes back to the same position by itself. So that is stable equilibrium. What happens in this case? Now listen here. Now the dipole is placed, it is opposite to the direction of electric field like this. Right? So for example, I have a dipole like this now. Right? Now if I disturb this dipole, it will not come back to its original position on its own. So now I can say this is not a stable equilibrium, this is an unstable equilibrium. This is a small minute difference between theta is equal to 0 and theta is equal to 180. So if I disturb a dipole, so which is placed opposite to the direction of electric field, so what happens? It will not come back to its own position. So this is unstable equilibrium. So for example, now the dipole is like this here. So I will disturb this. I will disturb like this. So one force will be acting like this, another force will be acting like this. So what happens? It will not come back to its own position. So what happens? Instead it will move like this. So this I can say when the dipole is opposite to the direction of electric field, it will be in unstable equilibrium. I hope you understand what is stable equilibrium and unstable equilibrium. Now we discuss about electric flux. So electric flux, it is represented by phi. So electric flux, it is represented by phi. What is this electric flux? It is the total number of electric field lines passing normally through the given surface. So I repeat, it is the total number of electric field lines passing normally through the given surface. So to understand this, let us assume a window is open, an open window. So the air is entering through a window. If the window is like this, so the number of air lines, I call this air as air lines, so these air lines are entering like this. And what happens? It will fill in the room. So the electric field lines, electric field lines that passing through the window and entering into a room, so once it enters into a room, it tells about the quantity of air that is filled in the room. So that is a scalar quantity. But the electric field lines are air lines which are coming through this window, so this is a vector quantity. So that is nothing but electric field intensity. So that means this electric flux, it depends upon two things. So one is the electric field intensity, and area. For example, if the intensity is more, intensity of air lines or electric field lines which is entering through the surface or an area is more, so the electric flux will also be more. If this area is increased, then the number of field lines entering through the window will increase, and again the flux increases. So the electric field line, electric flux depends on the electric intensity and also the area. So this is the electric field lines, right? And this is a small elementary surface. So here the number of electric field lines that is passing normally through a given surface is called as electric flux. Now you can see in this diagram, so the electric field lines which are linked to this surface is, so you can see here, you can count 1, 2, 3, 4. So the flux will be 4 in this case. But the same diagram, when you move on to this diagram, you can see how many electric field lines are linked to this. So it is 2. So here the flux is 4 and here the flux is 2. So that tells if the intensity is more, so what happens, the electric flux will be more. That means the electric flux, it depends on the intensity, electric intensity. And again, now if this area is increased, so what happens to electric field lines? The number of electric field lines that will be linking to this surface will increase. So that means it also depends on area. So there is a question, is area is a vector or a scalar? So we know we use that the area is a scalar quantity, but area is a vector quantity. So first we will come, before coming to this flux again, so let us see what is this area vector, whether area vector, and we will see that it is a vector quantity. So for example, to know that, so I have taken a parallelogram here. So PQRS is a parallelogram. So I want to find out its area. To find out, you see this length and this is width is making an angle theta here. So now what I do is, to find its area, I will draw a perpendicular here. So if I draw a perpendicular, so what will be, to find the area, so what I do is I draw a perpendicular, right? So this length into this perpendicular will give you the area of this parallelogram. So I think you have studied in your 10th class. So where A is equal to, so length L and this perpendicular distance is B sin theta. So area will be equal to LB sin theta. So we know that in a cross vector product, so A cross B can be written as AB sin theta. So here it is LB sin theta. So this can be written as A is equal to L cross B. So this area, now it is a vector quantity because the product of two vectors will be vectors. So this length is a vector and this width is also a vector. So along the unit vector along L or x-axis, it is given by I cap, and along B it is given as j cap. And what will be the direction of this area? It will be perpendicular to this, normal to this surface, that is k cap. So remember this, the direction of the area vector will be always perpendicular or normal to a given surface. For example, if I have this area, this is an area. If I ask what will be this, the direction of the area vector, so the direction of the area vector will be like this. So always it will be normal to the given surface, right? So now going back to this flux, now I told you if the area is increased, so what happens? The flux increases. So delta phi, it also depends on area. For example, I have a window, so what air is entering into the room. If I increase the area, that means if I increase the area of the window, that means I will open another window. So what happens? The air which is entering into the room will also increases. The air flux will increases. Instead, I am comparing with air. So if the electric field entering like this through this area, so what happens? There will be a flux, right? So the flux is the quantity. So now if this area is increased, the number of field lines which are entering will also increase. So that means the flux is directly proportional to what? Area. Now, and then there is another thing where the flux depends on. For example, if this electric lines is not linking to this surface normally. So in this case, what is electric field lines are, of the electric field lines are, it is normal to the surface, right? But in this case, the electric field lines are not normal. So it is making an angle with this area vector. If this is a case, so what happens? Now, this is the electric field lines and this is the area vector. It is making an angle theta. So this electric field lines or electric field lines will split into components. So one, it will be along this. So this will be E cos theta and other will be another component, that is E sin theta. Now tell me, so which component so we have to consider. So I cannot take E sin theta because it is like this. For example, if this is a surface, the air is passing like this. So according to the definition, it has to pass like this. So I cannot take this component. So the component I can take is E cos theta because now the electric field are moving like this. It is normal to the area vector. Now, so then that means this also depends on angle, correct? So for example, if I have this is a window and this is the air lines which are coming inside. So if this is like this, so it will enter easily and it will fill in a room. But if I keep a window like this, so air lines are entering like this. So it is just passing, it is not passing through the window, it is just touching and moving. So the air will not fill here, right? So that's the case. That means it also depends on the angle. Now, so from this we can write the flux depends on the electric field intensity and also the area. So therefore the flux can be written as it is E delta S into cos theta. So delta phi will be equal to E delta S cos theta. So next, so we know delta phi is equal to E delta S cos theta. So this can be written as, right, this is in the form of A dot B is equal to AB cos theta. So this can be represented as a scalar product. So delta phi can be written as E dot ds. This flux is electric flux is a scalar quantity, right? So what is the SI unit of the flux? So we know the electric field intensity. What is the SI unit for that? It is Newton per coulomb. And what is the SI unit for area? It is meter square. So the SI unit for electric flux will be Newton meter square per coulomb, right? So now let's move on to another thing. For example, if the given area is divided into small area elements, each of area delta S. So what they are doing now, if the given area is divided into small area elements, each of area delta S. So how to calculate the flux? So to do this, so this area is being divided into small elements of each of area delta S. You can see here, right? So to get the total flux here, we should know what is the electric field at this point and what is the direction of the area vector. So the area vector at this point along this direction, and electric field also it is along the area vector. So what is the flux here? The flux will be again E delta S. So like this you have to calculate the flux at each point, each area element, and then you have to add up. So if this area is divided into small elementary areas as such, so the equation becomes the summation of delta phi will be equal to summation of E delta S cos theta, or delta phi is equal to, it is summation of E dot ds, right? So for example, if this area is divided into a small elementary areas, each of area say delta S, then what I have to do, I have to calculate the flux of each area, each elementary area, and then I have to add it up. So then the equation becomes delta phi is equal to the summation of E dot delta S. Now this equation will be appropriate. So if you take a limit delta S tending to 0, and we can write this in integral form. What is that? The total flux will be equal to integral of E dot ds.